Good morning, everybody. We are going to do, for this week, 4.5. It's kind of a section that we're starting on. It's our last one before we do 5.1, and then we'll take our test. But what this is going to be about is really kind of a review from the very beginning of this chapter when we were actually still in school. All right, this is going to be exponential growth and decay with context problems. The difference between what we're doing now and what we did earlier is we're not using that PERT equation. That PERT equation was what we did for continuously compounding interest, if you remember. All right, now we're going to deal with the exact same equation. All right, this A equals A naught times E to the KT. That's exactly the same as A equals P times E to the RT. Same equation, just using different variables or different labels. All right, and this is just extending it to things outside the financial investment opportunities, right? So anything that's growing is going to be growth, where our K value, what we're going to notice is that K value is going to be positive. And if we're decaying or we're decreasing over time, our K value is going to be negative. And those are going to be the two differences between growth or decay. Okay, so let's look at a couple examples. Again, the only thing we're going to have to really worry about is this equation here. This equation here is going to tell us how to do pretty much everything. All right, so let's gather what we know. If we look at this question, at noon, the culture of bacteria totaled 2.5 million members. By 3, the population had grown to 4.5. How long will it take to be at, I should switch this. I changed the rest of them, but this is actually 8.1 million. All right? And so we're going to know how fast is this growing. We want to find that growth constant K, and then we're going to use that to extend and find for this 8.1 million. All right, so first thing you're going to look at is I'm going to go ahead and talk about 2.5 million. So I'm not going to plug in all those zeros. I'm just going to use 2.5, 0.45, 8.1. All right, and based off of what we know is, let's say T is time after noon. Right, that way we don't have to have too big of T's. This first example, we can see that when T is 0, our amount, which is our population in this case, is 2.5 million. All right, we can do the same thing because we know when T is at 3 o'clock, which is 3 hours past noon, our amount is 4.5, and we want to know what does T equal when our amount is 8.1. And so that's what we're going to be working on for this example, right? So we're going to use this A equals A naught times E to the KT equation. All right, our A naught is when T equals 0. All right, so that is 2.5. So our equation is really A is equal to 2.5. We always want our initial condition so we can get that A naught. So we can actually go over here and label this A0, E to the KT. Right, this is what it's growing by. And what we found out, though, is when T was 3, our A was 4.5. Right, so we can set up the equation. 4.5 is equal to 2.5 times E to the K. We still don't know that. Times 3. That's the piece we don't know. All right, we're going to use our solving techniques that we've been working on the past couple weeks to solve this, right? So the first thing we're going to do is divide by 2.5. Right, we want to isolate that exponential. Okay. And we get 1.8 is equal to E to the K times 3. All right, remember, anytime we want to undo that exponential, right, our process for that is just taking the natural log of both sides. All right, so we can make this equation, it actually becomes the natural log of 1.8 is equal to the natural log of E to the K times 3. And on this left side, we have just a number, right? The natural log of 1.8 is about 0.588. The natural log of E to the K times 3 is actually just K times 3. So if we want K, we can just divide by 3 on both sides, giving me that K is about, we don't have an exact answer, but it's about, and I've already rounded a little bit, 0.196. Fine? And we're going to use that as our k value in our generic equation to find out what happens when are we going to equal 8.1. Right, so we do that by just setting up a new equation to solve. Okay, so we want to find out t when a equals 8.1. So we're going to use the equation, well, I know a is 8.1. My a naught was 2.5. My k is 0.196. And my t is the unknown. All right, so we repeat this exact same process that we did over here. We divide by the 2.5. Let me do that real quick. We get 3.24 is equal to e to the 0.196 times t. When we take the natural log of both sides, we get the natural log of 3.24 is equal to 0.196 t, which gives us 1.176 is equal to 0.196 t divided by 0.196 divided by 0.196, giving us, let me come up here so I can have room, t is about 6 years. Okay, it's actually 5.999, I'm repeating, but I will call it 6 years. The next problem, zoom back out, is exactly the same idea. It's going to be the exact same problem, except for now we're going to look for the k. Okay, and this one just actually wants us to find the model. It doesn't have that additional question, so we're really just looking for that k value. All right, so we're going to use this fact, 5,714 years for half of the original amount to be left. This is what we call a half-life. All right, and what this tells me is doesn't matter how much I start with, right? So a naught is not given. We just know we're going to have half of it. So I'm going to take the easy way out and say, let's say a naught is 1. All right, so then I know my equation is a is equal to 1 times e to the k t. And I know that after 5,715 years, my a is 1/2 or 0.5. All right, so I have the equation 0.5 is equal to 1. I'm actually going to get rid of that 1. E times k times 5,715. All right, and now we just do our natural log stuff. All right, so we take the natural log of both sides. The natural log of 0.5 is going to equal to 5,715 times k. The natural log of 0.5 is, if you notice, this is where we're going to get a negative number, negative 693, divide by 5,715, we get k is equal to a very small number, approximately negative 0.000121, meaning our equation a is equal to a naught, get that, times e to the negative 0.000121 times t. All right, and this is how they can find the amount of carbon on anything after a certain amount of time. Right? And really what this is what we use to carbon date things. Right? If you know how much carbon something started with, you know how much carbon it has now, you can use that to solve for the time it took, right? So if you know it has about 20% of its carbon, you can know how long it took to get to 20%. It's going to be, in the tens of thousands of years. On the next page, we have a couple problems that you can work on. Go ahead and try these out. Go and circle the B's as well. Try these out on your own. The answer keys will be posted on Schoology later this week, probably tomorrow.